Hello, everyone. My name is Robel Askadom. Today, I'm going to present this article, Advanced Predictive Control, Insight from the Maze Exploration using Markov Decision Process. We prepared this article with Professor Korpichuk from Warsaw University of Technology. So in autonomous navigation is a very, very important part in mobile robotics. So to address this one, we can use either different traditional maze exploration algorithm or machine learning. We preferably use here a Markov decision approach. That is because it's very good in decision making and determining the final and optimal policies to determine our next moves. And also, we also find out that predictive control algorithms, such as the MPC, can also have the features to enhance the problems or the limitations that Markov decision process has. So it could be also enhancing the trajectory tracking. And also in here, what we also determined is Markov decision process is also comes with some limitations like to address real-time environments. And in this regard, predictive control algorithms could also have very huge impact on this regard. And so this is to enhance the maze exploration by addressing the real-time adaptability and also trajectory optimization, which is the very and the important limitation of the Markov decision process. So in Markov decision process, we have set of characteristics to be determined. For example, in a given environment, we have set of states that are this set of states are represented by S, and also as it is already need to be taken some action by the agent. So A represents the actions that are the possible actions that agent is possibly taken regard to the current state, and also we have a possibility of the agent that could be moving all around of different directions. So this P represents the transition probability, which defines the probability of reaching the next state. And also, as it's reinforcement algorithm, we have reward. So it's represented by R. So the reward is it's like scalar reward to each state action pair. And then also we have finally the discount factor, which is also determines the importance of future rewards. So as in Markov decision, we have some dynamic programming algorithms to compete for the final optimal policy. There are two the dynamic programming approaches, which are the while iteration and the policy iteration, to be competed in order to reach the optimal policies, which leads to the highest possibility sum of the feature rewards on each state. So as you can see in this picture, we have set of calculations which determines the possible final outcomes. Finally, where we are determining, okay, they are reaching in the final state or a final optimal solution. So having said this, Markov decision also have its own limitation. One of the big limitation of this Markov decision is computational complexity, as it's really unable to determine in real-time applications. For example, applications where environment has its own dynamic properties, Markov decision has some of the limitations to be addressed here. So that's why we are need to be focus some of the features that need to be added to this model in order to have a better optimization and a better solution. So one is predictive control algorithms such as this MPC. And in here, we have to address that, solve an optimization problem, not only by addressing some of the features, but also to introduce some features like the cost function, which minimizes and also determines the feature state by giving state. So this also helps if there is a possibility of deadlock of the agent or robot in a given status using the Markov decision. So which also is a very good thing to enhance the efficiency of the robot. So the minimizing cost function to the system constraint will also determine one of the features of predictive control algorithms. And also, for example, in environment where there are moving obstacles, a Markov decision process is very limited here to address that kind of policies. So enhancing some features is very important. So that's why we are needed to use with different algorithms such as predictive control. And the other thing is, as we said, is not only objects avoidance or obstacle avoidance, but also multiple robot coordination, which means there could be more than one robot could be also moved around or just explore around the maze without having any problems. So this is also cannot be determined using MDP or the Markov decision process. Rather, we can have some additional algorithms, which advanced algorithms like the predictive control algorithms is also vital here. So the hybrid approach, which is the combination of both like the predictive control algorithms and MDP, which could also generate optimal policy for navigation, which help us to determine not only the limitations, but also for better features, which could also open some of the research approaches for the future. So in here, MDP executes policy, of course. We can determine optimal policy, but in what cost is optimal policy? What is the limitation of the MDP also needs to be addressed. So that one is the computational complexity. So to eliminate this problem and to reach in a very optimal, the optimal policy in a very early times, we could have this hybrid approach. So which could also help us to adapt the real world environments, which could be dynamic environments with environments has moving obstacles. And also integration of enhanced trajectory tracking in dynamic environments is also a very vital thing to address here. So that's why we are coming with the approach of like hybrid environment proposals. So in our case study, to explore the maze, we have been using two scenarios. One is to use a physical robot in a very small maze, and also one bigger robot, bigger maze to be implemented virtually. So in the physical robot, we have been using different components, which are very vital to develop our robot. So we use ASP32, a microcontroller, as our main microcontroller in our robot, and along with different sensor like ultrasonic sensor and also some camera modules. And then this camera module is actually separated to enhance a very good localization mapping approach, because we are not unable to do it using different approach like the SLAM algorithms. We rather use the camera module approach to have some visualization. So in this regard, this camera module is incorporated with some devices like Raspberry Pi for better operation, and for some other additional operations like the object detection and also image processing. So we have this camera interface to our microcontroller using Wi-Fi. And we have other components like the dual shaft DC motor. We have two dual shaft DC motors along with the two K-star wheels to support our maneuverability. And also we have motor driver modules like two DC stepper bridges. And also we use 9 volts battery here to able to help and also to power our whole setup, and along with some of the servo meter to help to scan our ultrasonic sensor in different directions. So are our hardware components. And whenever we come with the software components, in the software approach, we have been using two very solid operations. One is policy iteration, which is the very important part of the project, which means like it's just like calculates the Markov decision approach, and also guides the robot movement, or decides or instructs the robot movement. And the other thing is the localization approach, which is have been done in the camera module, which help us to determine the image processing using the Python and C++. So in this one, not only image processing and object detection, also it helps us to determine the module, like to learn on train our model using the conventional neural network like YOLO. So these are the two things. And for the policy iteration, we use C++ and C libraries and C algorithms to define our algorithms. And in the experimental result, we have converged in 11 iterations in the 3x4 maze. With this 3x4 maze, which is this physical maze, has one cell, which is one cell obstacle, and two terminal status. In the 6x8 maze, which is the virtual exploration, has 9 obstacles. So in these obstacles, we are able to reach the optimal state after 19 iterations. In this regard, what we have been achieved is a very great optimization, because let's say that this 3 times 4 maze is 4 times smaller than the 6 times 8. So in the 3 times 4 maze, we have 12 states, but in 6 times 8 maze, we have 48 states, which means the 6 times 8 maze is 4 times bigger than the 3 times 4. So if this, like with the system is scaled linearly, the maze exploration would be expected to iterate 44 times in the 6 times 8. So its terminal state would be reached after 44 iterations. However, we reached 19 iterations because we are incorporating our MDP with traditional the left-hand rule maze exploration algorithm, which means it allows us to remove or eliminate some possibility deadlocks where the robot gets in some between 2 blocks or 2 obstacles. So because of that, we are able to reach our iterations after 19 steps, which means we are achieved optimization calculated more than 56%. So these are our achievements here we need to address. So our results here in discussion. So we effectively generated the MDP policies, but of course, the MDP struggles with the real-time challenges. For example, for image processing, there has to be some possibility limitations need to be addressed, some such as the light effects on the given environment is also one of the challenges. So to address this one, we rather have some other features, like, for example, instead of a camera, we can use we can have some sensor fusion, like using some LiDAR sensors to address or to have some better localization approach. And also MDP possibly not improve the adaptability, but also the execution. So the possibility that the time takes to execute and to the physical robot to explore is has its own delay because of the some limitations. So and like this Markov decision process not only help us to determine the possibilities, but if we are governed it with some predictive control algorithms, it will help us to fasten or speed up the execution process. So the computational speed increases with the maze sizes, of course. So as the number, the size of the maze increases, the computational complexity also increases with that. So which for this means like it becomes at some point it becomes impossible to determine or to explore our maze using MDP. Because of it minimizes the efficiency. So it's an inevitable that we need to address this one using these predictive control algorithms. So as a feature environment, we can hybrid the MDP with the predictive control algorithms like MPC. So we can also choose a better like reinforcement algorithm to collaboratively use with the predictive controls. And also, as I said, some sensor fusion algorithms like, sensor fusion approach, like to have a better localization, like LiDAR sensor in our hardware setup. So as a conclusion, we are MDP maze exploration shows a promising approach, like for especially in very small maze environments to determine our optimal policies. So whenever if we are integrating with the MPC, we can have a better option, also a better approach to explore in different bigger environments, especially in real world environment where there is a bigger mazes. So there is possibility we can also achieve a better solution by integrating MPC. So we can make it MPDP more important, more feature-based approach. So as a feature research in the optimization and with implementation, we can also implement, as we say, some sensor fusion and also enhance some of the hybrid approaches of MDP with some other predictive control algorithms or control algorithms in general for better solution. So that's all. And as a reference, we use different references, but mainly we are rigorously using these 3 books as our reference to develop or to prepare this article. That's all. Thank you very much for your time.